Who's Cramer? I don't know why this has to be. This probably doesn't have to be brought up. No. Too late now. We have to do it. X, Y, W. No, well. What if I just put 0 here? Let's look for Cramer's rule. Oh, it's just one M. That's too complicated. Cramer's rule is a way for us to solve for a system of linear equations. And if you look at Cramer's rule here, they talk about determinants, and then see, even this is more complicated than I want. I want just 2 by 2. Chilly now? That's what it says. Okay. Okay, here it goes. So you have a system of linear equations, and what the Cramer's rule allows you to try to find the solution to a system of linear equations kind of quickly with matrices. And what we have here is A1x plus B1y plus C1 is equal to C1, and A2x plus B2y is equal to C2. And what they have you do is they have you construct a coefficient matrix, which is just the matrix for A1 and B1, A2 and A2 and B2. And then they construct what they call the X and Y matrices, where they replace one of the columns with whatever is on the output here. Right? So they replace the first column, A1 and B1, they replace it with the outputs here, C1 and C2. And then for they call the Y matrix, they replace that, the second column, the Y column, with whatever it is equal to on the other side. And to actually find the X and the Y, it's just the determinant, determinant of the X matrix divided by the determinant of the original matrix, determinant of the Y matrix divided by the other one. Okay, so that's Cramer's rule. Right? So according to Cramer's rule, the solution to this is X is going to be the determinant of the A, B, D matrix divided by, or that's in the bottom. And then the top matrix would be the X column over here, the AC column, being replaced with this. So 0 and E. And then B and D. And these are determinants, right? So we got, this is 0, this is the number 0, so we got 0 times D and then E times B divided by this thing. Well, we can figure that out. This is AD minus CB, BC. Cramer's Rule. You guys did this when you were in high school, right? 8th grade? No? You guys did this when you were in 4th grade? 1st grade. That's what I thought. Yeah, well, yeah, I mean, these are systems of linear equations that we're solving for. And then this is for the y, the same denominator, A, B, C, D. And then here you replace the y vector, or the y column. So AC, the x column stays the same. The other column becomes 0E. Oh, AE. And then the other one's gone. Okay? All right. So I just wanted to do this. We can move on now. Thought I'd sprinkle a little linear algebra in your life. All right. So our next. Wait, does this look familiar? Does it look like anything that we might have done? What? What? Kind of looks like a Wronskian. How does a Wronskian look like? It's the what? It's the fundamental solutions with derivatives. What? y1 prime. What? I don't know. There's no question. Well, if you can see it, good. If not, then we'll worry about it later. All right. So, what have we been doing in this class? I get confused between this class and the other class. What are we doing in this class? We're doing. What's the last thing we did? Variation of parameters, right? I think I have my notes up here. I can always look back. Oh, we did Cauchy-Euler equations. What did we do before that? variation of parameters. So we were doing this, right? What? What? Well, you have to find two more determinants? Hey, yeah, this looks kind of similar to the Cramer's Rule thing, huh? How is it similar? So this looks like the Cramer's Rule we were just doing. We got the W1 and W2, and then the W, which is equal to this. Let's see if we can backtrack our pieces together. We got this defined to be our W. We got our W1 and W2 defined by this. We have what we're calling our U1 prime and U2 prime equal to this. Right? So if we take a look at, if we backtrack to Cramer's Rule, right, we must have been looking at an original system of linear equations that instead of an x and a y, I have a u1 prime and u2 prime. Right? So this must have been my matrix, my coefficient matrix, my A, B, C, D, and this must have been my 0 and E. And this must have been my variables x and y. So we can probably recover our system of linear equations. So this is equal to the 0. This is y2. Oops, this is prime. So if you imagine this is ax plus by is equal to 0, cx plus dy is equal to e, this is exactly what we were solving for. So this system of linear equations came along the way where we eventually got our Wronskian stuff. Is that okay? Now let's take a closer look at W1, because W1 we always created this matrix and we found the determinant of that, right? But if the format of W1 is always going to be the same, it looks like W1. I need to get rid of this page. It looks like W1 and W2 would actually be simple, right? Simpler looking. if we really just kind of thought about it a little bit more. And it's always going to be the same. If this is our general formula, we always have a 0 in f of x for the first column, and a y2 and a y2 prime. So this looks like it's going to be negative f of x, y2 of x all the time, right? And then W2 is always going to be y1 times f of x positive, and then the other part is 0. So it looks like it's going to be like this all the time. So instead of trying to remember the Wronskian, which was convenient for us, right? Then this would be, I don't know if it'd be easier to remember, but you know, it's there. And why not look for W as well? So y1 of x, y2 prime of x minus y1 prime of x, y2 of x. Okay. So the idea in the next section is that they're just reformulating a lot of what we've been doing already to have us come up with a simpler, maybe, procedure, if you can remember, memorize more formulas. But all these things come from the Wronskian. All these things come from matrices where you find the determinants of these things, right? But what they did was they ended up creating some interesting formulas where there's some theory behind those interesting formulas to help us solve for these differential equations. So the next section that we're going to talk about is called Green's function, and Green's function implements a function where you kind of start not forgetting about this, but kind of putting it in the background and dealing with functions a little bit more. And it also gets us to jump to solving for IVPs, initial value problems. And we also have, we will also have a way to find or solve for boundary value problems, BVPs. All right. There's my document here. My document disappeared. Document doesn't exist anymore. Uh-oh, what happened? Oh, should I save? So, Green's theorem, or Green's function, sorry. So what we're going to focus on at this point is just a second order differential equation, linear, and the non-homogeneous component. And then we're going to also take a look at the initial value problem. But this is our general setup, and this is more or less a recap of what we were just talking about. That your U1 prime, and this should be U2. your u1 prime and your u2 prime can be simplified a little bit to make it look like this. But we still have to take one more step, and we're interested in finding the original u1 and u2, so we would need to integrate this, right? So we would integrate this, and let me string it up from here where the particular solution you're looking for is going to be y1 of x. And now I need to integrate the u1 prime. So u1 prime. Now, if I'm going to integrate with respect to x, I can write this in terms of x, but since now I'm kind of watching out for initial value, I'm going to want to evaluate this from some initial value to some x value. I don't know if that makes sense, but what I'm trying to say is I'm going to want the limits to be values of x. The initial will be the x naught, the initial part of the initial condition, and then the upper limit would be the variable x. Now, you know, with integrals, if I denote the upper limit of an integral to be a variable, that means I cannot use the same variable inside. So I'm going to use a dummy variable t. So I'm going to take my u1 prime, and I'm going to just change the variable to t and make them all functions of t. So minus y2 of t, f of t, divided by w. Now that Wronskian is that, you know, y1 times y2 prime business, but I'm just going to keep it as a w, so I don't have to write all those things. And again, I'm going to change the variables inside of w as t's. And so if I integrate this with respect to t, and then I evaluate it from x naught to x naught to the variable x, then I'll get my function, and this would be this would satisfy my initial conditions when I start talking about initial conditions. So that's the first one, and then I have plus, and then I have a y2 of x. Integrate again from the same deal, from x naught to x of y1 of t times f of t divided by the Wronskian as a function of t dt. Okay, so far? Now, the integral is an integral with respect to t. I have these functions outside of the integral that have no t in them, right? So they don't have a t, so with respect to this integral, they must be constants. And constants, when you're integrating, usually you take the constant out. But on some rare occasions, you might want to put the constant in. That's what we're going to do. We're going to put this constant in. And by doing that, we really then just have one big integral. Right? So I'm going to put this constant in. The first one, I'm going to have a negative y1 of x. That's a function of x. Whereas the rest of these factors are going to be functions of t. That's y2 of t, f of t, divided by w of t, plus, that's the y2 is a function of x, y1 of t, f of t, divided by the Wronskian as a function of t. So in terms of us trying to evaluate integrals, normally we want to break it up and take the constants out. But we are looking at an integral, two integrals that we can potentially put together into one big integral, and that's what we're doing. We're kind of doing backwards to establish some nice formulas and functions and things like that. All right, there's a little bit more that we can do here. We can note that f of t divided by w of t is a common term or common factor in both of these terms. So we can imagine factoring them out. And if we factor them out, what we're going to have left is a couple of terms that we're kind of adding and subtracting. Now, you just have to be careful about those couple of terms. One of them is a function of t, the other one's a function of x. So, yeah, a little awkward. And just for convenience sake, if I just switch the order so the first one's not negative, and for some reason I switch the order so that y1 is first and y2 is second. Then we have something that's a little bit more compact. Okay? So it turns out that this business over here is defined as Green's function. And let's be a little bit more specific. This is Green's function for IVPs. And the notation is G for Green. Now, Green's function is actually a function of both x and t. So we'll put x and t as the function, and it's equal to this big mess. Okay? So apparently this is going to help us solve initial value problems. Yeah? Oh, that's inside of the, did they define the, oh, they put that, okay. So they decided to keep the f of t out, and then, okay, let's do that. Sorry. So let's put this as part of Green's theorem. Yeah, that would make sense because the Wronskian has y1 and y2 in it, so they keep all the y1s and y2s. So that is going to allow us to write your integral as an integral from x naught to y naught, or x naught to x. Green's theorem, or Green's function, which now we're redefining or defining properly to include the Wronskian. So Green's function has all the information about the Wronskian and about the homogeneous portion of your differential equation. And the only thing that's not included there is the function, oops, this is a function of t, is the function in the non-homogeneous part. Okay, so this would be your particular solution for your differential equation, the yp. Not the particular solution, it's the particular solution that you would add onto the homogeneous solution. Because you still have the homogeneous solution problem in business. Okay? So the idea is that once you know the solutions to your homogeneous differential equation, you would go ahead and find Green's theorem, Green's function. I keep saying theorem because it's in Calc 3. You would just find Green's function, and then if you change your f at any point, then your integral is going to change your f, and then that's how you're going to get your different values. Okay. All right. So I suppose we should do an example of using Green's function. Let's try the first one here. Y double prime minus 16y is equal to f of x, where they don't tell us what f of x is equal to. And they want us to find a particular solution. So, what do we need? We need Green's function, we need the Wronskian, and all kinds of other stuff. So, first we need to figure out what y1 and y2 are equal to. So, we do that. This is not the Cauchy-Euler, right? So, this is just a regular variation of parameters. Start off by finding the homogeneous differential equation. We find the auxiliary equation, m squared minus 16 is equal to 0. So m is equal to plus and minus 4. So our y1 is equal to e to the, do plus first, minus first, e to the negative 4x, and y2 is equal to e to the positive 4x. Okay? So, do I have Green's function? So we want to figure out Green's function. And what is Green's function going to be? So Green's function is y1 of t, y2 of x. Oh, let's figure out the Wronskian first. So w is equal to e to the minus 4t, e to the positive 4t. This is negative 4, e to the negative 4t, and positive 4, e to the positive 4t. And so e to the negative 4t times e to the positive 4t is just e to the 0, which is just 1. So I have a 4 minus 4, 108. So our Wronskian is a nice constant. It's just equal to 8. Okay. All right, now for y1 prime or y1 of t, I need to, so Green's theorem, or Green's function is going to be e to the negative 4t times y2. This is e to the positive 4x minus y1 of x is e to the negative 4x times y2 of t, e to the positive 4t, all divided by 8. Well, it looks like the factoring won't make too much sense. But we have exponents, exponential functions, right? We could probably write that into one thing. So wouldn't this be e to the 4x minus t, or minus 4t? Minus e to the negative 4x plus 4t all over 8. Yeah? Okay, well that's cool. And since we can't really, we don't know what f is, according to our formula, this is just going to be the integral from x naught to x of this function. You know what? Are you guys familiar with being able to rewrite a function that looks like this into something that something else? All right. Before I put the answer down, let me introduce you to a function that a lot of calculus teachers kind of just don't do if they're math people. If they're engineers, then they definitely go over this particular function, but if they're not, then they just don't care. That would be me. I don't care. But it seems like it might be handy here. Have you guys heard of the sinh and the cosh functions? These are the hyperbolic functions, and they're defined a certain way. So the sine, hyperbolic sine of x is defined as, you guys familiar with this? It's e to the x minus e to the minus x divided by 2. And then the cosh is e to the x plus e to the negative x divided by 2. So in seeing this function here, Green's function that we came up with, it kind of makes me think of the hyperbolic functions, right? If we just tweak the numerator, or not the numerator, but the power a little bit, where you have 4x minus 4t for the first one, and then the opposite of that, then we can treat this as a sinh function. And 8 is 4 times 2, so we'll take out a 1/4, and then now this is divided by 2. So we have the sine hyperbolic of 4x minus 4t. It's a little easier to write than having that big mess. Actually, let me check my hyperbolic definition here. Okay, looks good. Being like I'm one of those math professors that don't care about hyperbolic functions, I should check to make sure that's correct. By the way, we can go off on a tangent here and talk about some other sine and cosine stuff. That's not fun. Off on a tangent, like the tangent function. Anyways, here's my tangent. Has nothing to do with the lecture. This is kind of cool. Now, it kind of mimics the hyperbolic functions, but this, if you want to take a look at this and then show that this is actually true, just think back to Euler's equation where we had e to the I x is equal to sine and cosine stuff. And so if you work that out, solve for sine and cosine, then you're going to get this. Kind of neat. Anyways, that's my little side note. So we're really focused on this. And being now that our Green's function is this function over here, we can simply put that up on our answer. So our y particular is going to be the integral from x naught to x of the g of xt, which is a 1/4 sine hyperbolic of 4x minus 4t. Times, remember this is g of xt times f of t, and f of t we don't know, so we'll just have to, and the t and the x, remember you got to get that straightened out. If you put the wrong variable in, then it's going to be incorrect. Since we're treating this as a variable of t, we're going to need to put in f of t, not f of x. So x is constant with respect to this integral antiderivative, and t is your variable with respect to this derivative or integral or antiderivative. And if once you know what t is equal to, then you can solve for this. Okay? So that would be your y particular for this particular problem. Questions? Okay. Yes? Yeah? They would, if they were going to give you an actual application or an actual problem, they would give that to you. Like in the next batch of problems here, they will give you FT. So, point in doing something like this is that if you happen to do a problem that's similar to one that you've already done, then you're kind of a step ahead, right? So let's say we're doing number 7 now. Where the homogeneous portion is exactly the same, except instead of an f of t, we have the actual function. Then we should be able to solve for this. So let's see if we can solve for this one. And what I'm going to do is I'm just going to steal what we've already done. Borrow. we already know the y particular for this for generic f. So instead of going through that big mess again, we already know Green's function for this. So now all we have to do is calculate or find this integral. So to find a particular function for this, yp should equal to the integral from x naught to x 1/4 sinh 4x minus 4t times x e to the minus 2x dx. Oops, t, yeah, thank you. Fell asleep there. Now, I know we went to sinh to make our integral look a little bit easier, but since I'm multiplying this by e to the negative 2t, I might consider going back to the exponential functions again if I were to actually have to compute this integral, or, yeah, antiderivative. So we're done with this problem because we kind of did all the work already. And I mean, this is homogeneous parts the same. This is your f of x, and so. Okay? Yeah, and in this particular problem, they say find a general solution for the given. Oh, they want us to find a general solution. I guess we're not quite done yet. Use the results obtained from 1 through 6. Do not evaluate the integral. So if they want the general solution, then we have to provide the other business, the homogeneous portion. So let's do that. Yeah, so let me rewrite our y1, which is e to the negative 4x, and our y2, which is equal to e to the positive 4x. And so our general solution is going to equal to c1 e to the minus 4x plus c2 e to the positive 4x plus, now all this stuff, the y particular. I'm going to rewrite everything over. So there's your solution. By the way, if you were to pump this through the integral and you evaluate from x naught to x naught is a constant and then x is a variable, this will eventually be a function of x, and the t's will all go away because it's a dummy variable inside of the integral. Okay, now we're done. This is the general solution. So let's see if we got, oh, they use a different function on us. Come on. Why would they use a different function? All right, well, should we make up a problem? All right, well, let's make up a problem. Famous last words. Let's see if we could do this problem here and then add some initial conditions to it. And let's keep the initial conditions simple for now. where y of 0 is equal to 0 and y prime of 0 is equal to 0. So now we have a complete package. We have an IVP where we actually have values for y of y0. Yeah, whatever. So what we want to do is we want to take a look at our solution, right? Our solution should look like this. Our general solution looks like this. What's important to note here is when we're solving for our solution, we need to solve for C1 and C2, and not only that, but we actually have to end up calculating this integral. And the only thing that we need to know about this integral is that our starting point in our antiderivative is going to be the starting point given in the initial condition. So whatever is inside of those parentheses is going to be your starting point for your x value, and then you'll have the general generic x for that one, for the other one. Okay? But we still need to solve for this business over here, and to solve for C1 and C2, what we're going to do is we're going to assume that we're solving for the homogeneous differential equation using these initial conditions. I hope that's not 0. All right, so let's solve for it. I hope it's not 0. I hope it's not 0. So we need our y, and we need our y prime. So y prime is equal to negative 4c1 e to the negative 4x plus 4c2 e to the positive 4x. So we'll use our initial conditions where we put 0 in for x, and we set both of them are going to end up being equal to 0. So in our first equation, we're going to get c1 plus c2 is equal to 0 because e to the 0 is 1. That disappears. We have a minus 4c1 plus 4c2 is equal to 0 for the second one, because the derivative evaluated at 0 is equal to 0 also. Now we can use Cramer's rule, right? Or you can just solve for this any way you want. What's the answer? Is it 4 or negative 4? What's C1 and C2 equal to? This is taking too long. It's all 0. Okay. No, I guess not. But that's okay, because this is gone, and now we just need to, the particular solution, we still can find a particular solution based on this. So that's gone, and now what's left for us to do is we need to figure this out. And this will end up being an integral, again, where your x naught is your initial condition, 0 to x of 1/4 times all this business. So this is now an antiderivative where I might want to go back to the exponential functions. Let me write it out first, and then we're probably going to be undoing what we did to come up with Green's function. So we're going to take a couple steps backwards. This is something over 2, right? So let's just call it a 1/8 on the outside. And this is e to the 4x minus 4t minus e to the opposite of that, negative 4x plus 4t times t e to the negative 2t dt. Then we can probably just put it into Mathematica. I'm going to go back to the cinch function. So the exponent is negative 2t. And we want to integrate with respect to t. And we're going to go from 0 to x. So we get a nice function. Nice, relatively speaking, a nice function. So if this is a nice function, kind of wonder what a not so nice function would look like, huh? So after doing that integral, then we would have this for our solution. Now, yeah, we could have tediously done this. We would have factored out an e to the 4x and e to the negative 4x because they're constants with respect to the integral. And then we would have broken this up to at least two integrals. And then you'll have to probably, because of that t sitting out here, it'll probably be integration by parts, and then just kind of crank that through. And then this is your particular, y particular. And this is the particular solution to the initial value problem that incorporates the initial value. Yeah. Having a 0 and a 0 for your initial value are our outputs here. Having a 0 and a 0 here kind of made this all disappear, because if you imagine this is, and we'll talk about the applications of this, if you imagine this is some spring that's oscillating, this is an external force for the spring that's pushing it, some machine or something that's cranking the spring, and you want to find the motion of that. If there was no machine there, and the starting point is 0, and the initial velocity is 0, then you're not going to move, right? Unless you have an external force that's pushing it around. So having zeros for your initial conditions would give you nothing for your homogeneous part. Okay, so this is half of Green's theorem. The other half explores the boundary value problems, where there's boundary conditions. Instead of just an initial condition at 0 times 0, there the boundary gives you conditions for the position at initial and some ending time, or gives you the velocity at initial and ending time. So we'll explore that next time. Okay? All right. That's it. Good luck.